Welcome back, guys. So yesterday we left off somewhere around here. Yeah, it's here. So yesterday we managed to actually switch between actually just the kernel and the interrupt handler because even that was not working yesterday. So at least right now that works. You can just see that. So bash build. So it was a pretty simple error, I guess, because right now, as you can see, we have timer interrupt fired, and then we have the running kernel, and then we have a timer interrupt fired. So what was the error? Was just that we forgot to. No, it's not actually forgot. It's like for some reason, we have our handler, which is the IRQ dispatcher, because this is the IRQ entry and we have the IRQ dispatcher. When we get into that dispatcher, we check if it is a interrupt, what's the ID of it, and we have a case statement where 27 is the ID. In that we have the IRQ handler that was added yesterday. Previously we had this print message plus this schedule on tick, which was actually supposed to, as you can see, set these values, that is set CNTV, which is actually going to update the because how ARM interrupt works is that we have a register, we set a certain value in it. When that value becomes 0, the processor will throw an interrupt. So it will keep on throwing if the value is 0, because these are the three conditions that we saw yesterday. As you can see, yeah, either we have to mask it or we enable it, or the value that is written it, which is the firing condition, is no longer met. So firing condition is actually the value being 0, and in our case we initially wrote a value and that value becomes 0, and we got the first timer interrupt, and then we never wrote to it, so it always kept throwing the interrupt. Because I was assuming when I'm calling this function, somewhere in this we should have set this CNT value, and because in all those cases there is a CNTV, because if we were inside this, even though we don't have anything, by the end of this there is a CNTV, and if we were inside this condition, there is a CNTV, and if we just directly came here, there's a CNTV. But what I didn't confirm is that, I don't know, for some reason this function just did not work. So when I added a print message inside set CNTV, it was never called after the first IRQ was fired, and it was pretty straightforward to fix it. I just called it inside. I added a function and I just called it inside it. So whenever we come to this case, we just re-enable it and then we go to schedule on tick. So in our schedule on tick, we no longer have to call this, because it's already called, so we can remove those things. Okay. Okay, now what? Yeah, next thing, let's go back to our. So as soon as I did that, the timer got back to its normal state, so it was able to fire back again when the value becomes 0, and until that our normal kernel code was just keep on running, because our kernel code is just going to do this endless loop, which was just for testing, which should never be reached, because we have to uncomment all this part. Okay, let's just uncomment those code and see what goes there. So we are initializing 2 tasks and we scheduling one of it as the starting task. How do we do that? Yeah, it's here. And I think as soon as we start this, we should never be able to reach this code. So let's just move this back here and let's just disable this, and we should never reach this code either, because we clear the interrupts, we say we are jumping and we jump, that's it. And kernel code ends here. It should never reach the kernel code. There is no kernel code, and there is only kernel code in interrupt handlers, and probably in case if we call kmalloc, we come into kernel code some way. Okay, let's see what happens. I guess there's enough context to. I also have to double check if my screen is still recording, because it happens quite a lot now, so I have to make sure. Okay, right now it's just keep on schedule getting fired. Okay. Let's see. This is the first tab. I have to switch to 0th tab. Okay. Sometimes it's hard to remember all the Temex shortcuts and VA shortcuts. Well, it's there's pretty. They don't collide. I guess they have some sort of idea that Vim will be using those, so we are not supposed to use that. Stuff like that. Also, the main control command is the key, so it's fine. Okay, for some reason, if we let our kernel keep running, and that is to say, if the timer interrupts keep on firing, the control C never reaches that, probably because there's no one to handle it, because there's always an interrupt. Possibly that's why we have to kill the entire window and restart it. Hopefully we can also put a pickle and camo just in case, and remove the camo logs too, because it would have been already filled. Okay, what else? Now it's time to just run it once for a little bit and just kill it as quick as possible. Bash build. I run it and I kill it. Oh no, I didn't even let it fire till that. Okay, that's good. So we have the job, and job is schedules, and we have timer IIQ that is keep on thrown. Okay, now let's come back to the error that we found yesterday. That is that we are using kernel address from EL1. Let's see. Schemo. Was it? Let's grab for all 5 characters of var and just give me the head. Yep. So this is the first error, and as I said, this error is supposed to be an access fault for this address. So it is a pretty straightforward error, and the error is that no, let's just update the to-do because we fixed that. Okay, now the set scene. Now the value is updated whenever there's a timer interrupt, and now we are switch between the kernel and the interrupt handler properly. Okay, PROPRLY. Okay, now to do is to find. So when we get into the user code, we are using the stack, using a stack pointer. There's a kernel address there. 0xff. Okay, what can we do? We have to check if we can add a separate what's that, table for every process, page table. This would be the best way, because as I know, every user process should have its own table. That way that process can use the entire virtual space. And then what else? What else can we try? Yeah, that's the first use case. Okay, also, first of all, whenever we switch, do we have to because let's assume a process is switching. At that time we put all the important registers back because we saved them and we restore them. Do we have to do anything else other than that? The main tables will be in a register, so that's just fine. What about the just by putting back the table, the virtual mapping should go into the kernels, the actual physical address. So because what I was assuming is that what I'm thinking about is that we have to code, this too will be placed inside actual physical memory and around 8000, and inside the kernel space they already have a virtual address, and we are jumping into this virtual address. So now we have to map this virtual either this virtual address or this physical address. Which one should I map? Because yeah, I guess I just have to map, add another table. In that table, I give a virtual address pointing to this actual physical address. Okay, that's fine. But what about the actual switcheroo? When I actually jump here, so what I do is that I take a context, I put that into stack. Where's it? I take a context, I put that into stack C, and then I move that pointer to as the top of the stack, and I just restore unread. Restore unread is just going to restore everything from this context into the registers, and then put eread, and then so eread is just going to take the return address from probably this ESR ELR1. So that would be the return address. So in that return address value, I should make sure I have something that is already mapped in that table. So I think only thing I'll have to add is a new entry here. That would be a table value. And then I have to fix every old code first of all. Yeah, no, I believe I need a snapshot here because I don't know what else could go wrong. Let's just say git status. Let's just remove camo. Polish that. What are the things that are getting added? What the fuck is this? I think it's fine. I don't need the WoW files. Git restore staged star.wo. Did I not add that into my git ignore? What the fuck? Oh, it's not here. Star.o. What else? .log. See. Okay, now they don't even come up. Oh, it still comes up. What the fuck? Okay, I have to figure out how to remove all those random stuff. Okay, it's fine. Let's just put a commit. Walking snapshot after interrupts walking between EL1 and handler context. Okay. What the fuck? Finally, I remembered my fucking password. Okay, what now? Let's see if it is just working. Okay. What do we do now? Now we have to fix the context.h with this TLB value. This is what we talked about, because it needs something. It can have ELR1, and let's add another one. And TLRP1. What else? Is there anything else that we might want to switch? I think it should be good. Now we have to set these defaults. Okay, wait, let's check where exactly are we setting those values. In kmain, if we go to init task, okay, we already have this. We need a user specific page table and store them into tbl0 respective page table. So because we do have this to do already, currently we only update these values. Inside the build context, we pass these stuff. Okay, let's see, ctx tbr real one. Currently, this is a process. This is a new process. So, and these values are supposed to be physical addresses. Yeah, these values are supposed to be physical addresses, not virtual. In that case, maybe we could just maybe we could keep a global yeah, something like this, but it is going to be only holding you. So it's UN64 star how do we declare an array? I fucking don't know. I guess it's like this. UN64 user tables. Okay. And a single table should have how much memory? Wait, every table should be a address, and that in the address we can have lots of stuff, so we need enough space for all of them. um should we go to linker or should we use dynamic allocation? I'm just wondering. And another thing is that uh, if we could allocate 1 GB block for every process, would that be fine? 1 GB block. So everything would be valid in physical level in those addresses, but uh, in the tables itself we can just give that, so we don't have to always add a physical entry. I mean, what does it mean to add a physical entry? You just have an entry in the page table, and that table needs to exist. So there needs to be a L1 table, there needs to be a L2 table, there needs to be a L3 table. So there needs to be 3 tables of 512 entries. So we need 512, 512, 512. So 3 512s for one table. So what is that? 512 into 3. So we need 1536 bytes of memory per processes. And we'll have, currently we are just going to have 2 processes. Maybe initially we should stick to statically registering this memory, and then once we get it working we can think about dynamically allocating it, because we don't have to go through entire debugging session just because we were not able to fix the dynamic allocation initially. Yeah, maybe it's better to just initially hard code it and then fix it. No, I don't know. I'm still wondering. So what I'm gonna do is that we're gonna allocate some new values, new locations, because that's also key. Because right now, as you can see, as it right now our kernel base is 8000. This is what our kernel is using. Its codes is getting mapped into that physical location. And what about our virtual space? Because we did change something in there. Yeah. And the actual, what is it? The dynamic our kmalloc, all its new addresses the whatever new addresses that is allocated by our kmalloc, that is going to be placed after C000. So even this block is already occupied. So now we have to come up with the next block, that is 1 GB after C GB byte after it would be extending to C to D000. Oh yeah, we can use that. Yes. I think we can use that. I don't know what exactly do we need. We need an actual space in physical where we can store our user tables, and a user table is only of 1500 bytes because we need 3 512 entry tables, and right now there's only 2 processes, so we need around 3000, let's say 4000 bytes. So it's like one page. That's the location where we are going to store our tables for the user space. That's fine. Now what else do we need? We also have to store the we also have to store the actual everything else, because the entire virtual space needs to be mapped into an actual physical address. So where is this going to be located? Maybe D0 can be the location where everything else is going to start, the entire virtual space. For any processes, it's going to map inside this D0 using some new kernel scheduler. I don't know. No, like then why not just use kmalloc for that too? Because kmalloc should be able to do that. Why do we need a separate space? Because in case we need new memory, we just call it and it's going to give us that virtual space. Yeah, I think that we don't need any separation. We only need a separation for that for the initial 4000 bytes that I was talking about, that's going to hold the actual physical tables. Okay, so currently my design choice is going to be, we are gonna let's write it down, only then we'll be able to grasp it better. So design we need a physical location to store the tables, user page tables. So that is of 512 into 3 size, and we have two user processes, and we need to map the user space into some physical address, and we need to keep track of that address too. Maybe we just reuse Kernel here. Maybe we hardcode this address. Okay, these are the possibilities. I don't see anything else that we are missing, because only thing that we need is the tables. And yeah, I think we are good to go. Okay. Okay, let's see. Where do we define it? Where do we define it? We just need some space. We just need 5,000 blocks. Nothing much. But do we have that kind of space? Because it's already really cramped, because we have like this is what we need. We need one table of the 4 KB and so 512 entries, and another table of 512 entries, and then another table of 512 entries. We don't need this table. Okay, we do need that table, so it's like 512 into 4. We won't store anything in the L1, but still I guess we need that table. So it's like 512 into 4. You need 512 into 4 because our main kernel is using these 4 addresses, and as soon as if we are done with this, I think we already used the rest of the space too. If we go into our, where is it, LD linker, where the fuck are you? That's okay. Yeah, we have our stack from F00. So we have to let's just align this. If we can move this a little bit away, we should be able to get more space here. And we can add a page table entry for it in our MMU. Yeah, let's just move it to 1F. and we should have everything after FFFF. And I think we won't have the page table entry for it. Okay, we still haven't defined that part either. Message. No, let's just fix everything and then start the debugging. So let's just start with this. We have updated that part. Probably we need the entry for it. How do we do that? We come here, we come to Ming, and we define something. Stack top. Top of stack. Link. Okay, we have that. Now what do we do? Now let's add that entry in MMU. I think I copy this. Paste it. We move stack top. Calculate L2 index for stack top and put that back. I think should be fine because the kmalloc starts after C, so we won't collide with our kmalloc location, and we don't have anything else around this space. I think it should be good. And what else? Let's see. And we also have to update the kmain with EL0 and EL1 values, which is what? This is going to be a hard-coded thing. Use define. Yeah, 0 0 0 UL. This is going to be our L0, and we can just add 1000 to it and get L2, L3 and L4. Okay, and define user processing 2.L0, and this would be user process you are fucking using define. There's no fucking equal to. It's a process L1 plus I think this should do the arithmetic if I put it inside brackets. Plus Xerox 1 it's 4,000. I'll just put 5,000 then. I'll put 6,000. 1 2 3 4 no 6 0 0 0. Okay, yeah, hopefully this just works fine. We can just do arithmetic operations to get the next else. Process table start. This would be better. Table start. Okay. Use the process table start. Okay. Now what do we do? Now we just have to give L1 table start. Also, I don't think we have to switch wait, I'm doing something wrong. If we go into our MMU, there is TBR1 and TBR0. Okay, so if we go here, TBR1, TBR0, okay, that's fine then. TBR0 should be allocated with this. What? Let's as it use the process 1 table start, and let's remove table because this is always going to be the kernel table, so it's let it be same for every processes. We just have to update TLB0 value. Okay, now what do we have to do? Now we updated it here. Now we have to update it inside kmain. Did we fix that? Yeah, we have updated it here as the user start. That is if IT equals 1 else user 2. Okay. There's only 2 processes, so this should suffice to fix this to make it get dynamic in future. Okay, what else? Now all we have to do is that we are calling two functions here, and we are passing stack. Yeah, we also have to fix that, because currently we are using kmalloc and we are just simply passing it directly to their kernel stack is fine, but user stack is not fine. So we have to add the table entries for this table. Inside this table, we have to update the table entries. Okay. And we also need a helper that's going to convert this kmalloc virtual address into a user space address. We are just going to have identity mapping, so I think all we have to do is that copy this function. Where is it? Yep. Yeah, this is what we want. We take something and we zero out it. Let's write that. What is it? It's supposed to be no, not void. It has to return event 64, and it's going to virtual kernel to user space, and it's going to take events 64 kernel virtual kernel address. Okay, virtual kernel address. Now we can just paste it here, and I think nothing much is left to do. We just have to put return virtual kernel address. We AND it with this, so we get the upper lower bits. Nothing much. I think then we could just put static inline. Okay, that would be better. Now we can make it compile time. No, we can't do it compile time. Okay, now we need to add an entry in the table. What sort of entries do we need to add? What sort of entries do we need to add? In case, let's take an example. Example is that, let's say the kernel user stack is supposed to For the user stack, let's say the kernel kmalloc is giving us f of 0 0 0 c something. Now what do we do? Now we need to map this into our user space. So in user space we call this kernel to user space. This would give us converted value that would be like 0x000 some c00. Now we need a table entry. We need table entry for this address to physical, and it's going to be an identity mapping. And how does it should look? It should look like 0x000 c0002 0x0000 c00. This is how it should be. This is the user space address, and that's mapped to physical address. And this address is actually managed by kmalloc. This address is managed by kmalloc. Bitmap. Right. Okay, what else? What else? We can add this entry. So if we want to add this entry, first of all, we need to check the L1 index, L2 index, L3 index. L0 index is always going to be same. And L1 index, we may not be sure. So let's not assume that L1 index will be there, because L1 index is, and indices are of 1 GB block. Still let's not assume that. L2 is 2 MB and L3 is 4 KB. So yeah, so let's add all of them dynamically for an address. So we need a helper that is not going to return anything. Map user to physical, and it's going to take one uint 64 address, because we only need one address, because they are going to be the same value, because we get the address from kmalloc, we convert it into a physical, and because the upper bits are 0, this is a valid user space address, and we can just directly map it to physical. Okay. And we need 3 blocks. We need 3 entries. Maybe we should write it inside this MMU, so we can reuse all the helpers. Yeah, we don't have to import them inside here. Okay. This is what we have to do because we need to, if we are gonna do it here, we also need to define those things here. Maybe I can just put it inside mmu.h. I think so. And we are using mmu.h here. Okay, so it should already be available here, and we can use it here too. Yes. We can just put we can just put okay, first of all we can clear the tables. Do we need to clear the table? Okay, let's clear the tables. First of all, we need 3 table locations. Events. What the fuck? What the fuck happens? Events 64 L0 is going to be user space table 1 start. That is fine. And events L1 is going to be L0 plus 0x 1 2 3 1 1 2 3 4. I believe so. That's how we put it, right? Yes. 1 2 3 4. Okay. And this is going to be how it's going to be for one L2 and L3. L2 and L3. Put L1 and L1, L2. And we are only gonna keep till this is of some big GB. This is I guess 1 GB. 1 GB. This is of 2 MB. And this is of 4 KB. Okay. If all our arithmetic operations are correct, nothing should go wrong. What else? And I should not always assume user processes as 1. Okay, then process ID event ID ID equals 1. Then I go with this, or I go with use the process to make this dynamic. Okay, what else? So we have 4 table values. Now we just have to add the entries. Yep. Now we have to add the entries. And this is the L1 entry. I should have added helpers. It would be so much easier to just call that. Now I have to just bring an entire block inside. It's just so fucking not looking good. What the fuck? Okay, something was wrong in that. That's why it didn't work. Why? There's some formatting issues. Okay, so we have L1 index. Calculate L1 index for L0. No, L1 index for address. And make a table for L1 base, which is just L1 in our case, and write it inside L0. So we have the L1 entry now. L0 entry. Now we need L1 entry. Where is the L1 entry? You have it here. I'm still too lazy to convert that into a function, which should be really good, because I'm just rewriting the same code, and yeah, I don't know. Even 64. And for L1 index, we still throw in the address. For L1 index, we throw in the address, and we make a table descriptor of table descriptor. So table descriptor is supposed to be for L2, and we write it inside L1. Inside L1, inside this index, we write a L2 table index. Okay, we finished L2. Now we need L3. Let's copy L3 from here, because this should be better. Because there, I think we may make it as a block after L0, L1, and L2. Yeah, L2s are blocks here. L2 is a block. I don't want that. I want L2 indexes to be another table. So let's just copy it from our old code. I'm just checking if it's still recording. This is our L2 code. We calculate L2 index, we make a table descriptor, we set the entry, but there's too much to see. We'll just copy and we yank it. We go back to our code here and we paste it, and it's an L2 index. And L2 index for address. And what else? And we don't need this stay block because this is not what we want to do. Don't want this either. And we have a L3 table. It's just L3. And we can remove this print. And inside L2, we write L2 index and a table. The fuck? Why the fuck is it not getting formatted automatically? Why does it go back? Okay, that is done. Now we need the final entry, that is the L3. And yeah, this is it. We come back and paste it. Paste it. And it should be address. We don't need this line. And it's a physical block, so it's still the same address because it's an identity map. And we have L3 table. Yep, we are done. Now we should be able to map any user process, user address that came from the Kernel lock. We converted it into some user space address, and then we mapped it. We make an identity map. I think I didn't give 4 spaces, that's why it fucked here. Okay. Identity map from user space to physical range. Okay, that's fine. Now we have to just map those things. Now let's just copy this and extend it, and let's just call it use stack equal to 64 13. No, it's just uin64. Kmalloc will return a uin64, and I'm going to convert to user to what's that helper name? It's kernel to user space. Put kernel to user space, and I pass this u stack t, and I also add that entry, that is map user to physical in IT, and address is u stack t. Now I also have added a map for that inside that table. Should I do this for anything else? This will be accessed from EL1 context, so this is fine. Only this will be accessed from EL0, so we need a map. I think that is it. Yep. Wait, what about context.h? No, not that context.h. Context.c or what? Where do we... Okay, we define it here. Okay, that's fine. That's fine too. In that case, one thing left to do is that inside our here we still have to save one more thing, that is how do we save it? Wait, where is it? Contact.h. SPL1 is inside, SPR is the final one. Okay, we just have to save one more thing. We copy this, we save TLB something as it this will also save this value. I think that should be enough. And then I guess we have to put this. CTX 0. SPREL1 is the final one. Okay. Set CTX and we put 30 star 8. Would it work, or should I remap everything from 35 to 31? I think it should work, because this is just for array accessing. In that case, should I go from 35 to 31 or 34 to 30? Maybe I'll try both cases and see which one works, because I just have to figure out how this will be pushed into the stack. So during the save stack, we subtract the total CTX size. Okay, what's the total CTX size? It's going to be 34 into 8. In that case, then I guess it's better to 35 into 8. This is the entire size. What exactly is 35? And this will be in 34th location, this will be in 33rd location, this will be in 32nd location, and this will be in first location. We save this context, and when we restore it, we have to first restore the final value, which will be the TLBR values. And we store it inside TLB. Nothing much. I don't think there's any other difference. Okay, I got that. I got it. This is the size. This is the 35th index. I guess 30 is already used. because we are using 16 bytes of 15, so that is the 30th bit is already used. So we can use the 31st, 32nd, 33rd, 34th and 35th. So I think this should work. And we are just restoring it here, and that should be fine. And finally we gave it like 35 into 8. Okay. Yes, this makes sense. This is the total number of 8 byte values stored in stack. Okay. What else? I think now it's time we are ready to roll, because what else do I have to fix? I have to fix it in this vector table, and I have to fix it here, and then yeah, I also have to fix the ELR EL1, because that location is also supposed to be user space. Yes. And what is the return address? Okay, entry is the return address. Okay, and we can convert the entry into thing. Entry would be definitely be a virtual address. So entry equal to, what is it, map user to physical. No, not map user to physical, kernel to user space, and virtual kernel address is entry. Now we have updated that value too, and we have to map that value in user space. So map user space address ID and entry. One more thing is that this is the start of the and we'll have 4 KB, and this function size won't be bigger than 4 KB, so I think this should be fine. If the function is bigger than 4 KB, which is not possible, we might have to update the entry +1, etc. Yes, we map one page from that starting address. This won't happen, I guess, because probably this page is just it's just 2 lines, so it definitely is not going to be 4 KB. I think we have did everything. Let's see, let's run it. What? Why is it kernel to user space, kernel to user space? Okay, I got to unc8 star. Okay, anything else? Okay, I have to map this as void entry. Is that even possible? I think we can, because that is also just a function pointer. We'll just map it into it should be what void entry void. I think let's put this star void expected an expression. What do you mean expression? How do we map a pointer, normal pointer, as a function pointer? What is a function pointer? Maybe we don't need this signature. Maybe we need let's see. I think if we make it this void star, it will automatically convert it into that pointer. It is possible, I guess. C does it implicitly. What's incompatible? Okay. The issue was in here. Shit show. I was doing a shit show here. It's just U in 64. What the fuck happened? Now it should work. I guess I should just read the error first of all properly. Now this conversion is not working. No, it still works. We just have to pass this in here too. Let's just UN 64. And because I have made it as void star, this should automatically be converted to whatever signature is here. I think so, because I remember reading somewhere that C does implicit conversion, and it's a bad thing because sometimes we don't know. Yeah, it works. Because right now, because we set it to void star, it automatically converted it into whatever signature this function accepts. This can lead to lots of errors because we'll never know what was actually converted into what. Okay, but then this should be enough because next time let's just to do. We have updated all the places with the table register to save and restore. We have added some helpers to convert the user maps. Now it compiles. We have to make it work next week. Okay guys, today we just managed to put things together because right now we have fixed we have added some helpers that are going to map the user's space address into actual physical, and we have some helpers to put back the address, because as you can see in our we have added this save during the save context. We have added this extra register that needs to be saved and that needs to be restored. And yes, I guess that is it. Yeah, let's see how it goes next week. Thank you guys. Bye bye.